While a scene cannot contain entities directly, we can load entities from what's called a subscene. A subscene is a scene that's nested inside another, and the feature called baking processes each subscene to produce a set of serialized entities. When a subscene is then loaded at runtime, it's the subscene's serialized entities that get loaded, not its game objects. Here, for example, in a project using the entities package, we have an ordinary Unity scene, and we can conveniently add a new subscene to it by clicking the plus sign in the scene window and selecting New Subscene. This creates a new game object with a single monobehavior called subscene, which references a newly created scene asset. While we could open and edit the scene asset directly like any other scene, we can also click the checkbox on the game object to open the subscene for editing in context of the root scene. Opening a subscene this way loads its game objects within the editor and triggers the baking conversion process. Unchecking the box closes the subscene and unloads the game objects from the editor, but the entities produced by baking remain loaded. When I add, remove, or modify game objects in the subscene is re-baked. So say when I add a cube game object to the subscene and set its material, the subscene is automatically re-baked, and what we see rendered is actually the entity baked from the game object, not the game object itself. Again, be clear that only the baked entities of a subscene are loaded at runtime, not the game objects of the subscene. However, if the game objects of an open subscene are modified while in play mode, the subscene is incrementally re-baked and the baked entities are live updated. For example, if I modify the cube game object's transform, the entity's transform components are updated immediately. In fact, any changes I make to the subscene's game objects while in play mode will actually persist after exiting play mode. Now, here's how the baking process works in detail. First, a baking world is created to store the entities created from the subscene. Second, for every game object in the subscene, an entity is added to the subscene's baking world. Third, for every game object component in the subscene which has an associated baker class, the bake method of that class is called. In these baking methods, what we can do primarily is add components to the corresponding entity of the game object. For example, the entities graphics package provides bakers for the mesh renderer and mesh filter components, and these bakers add the appropriate rendering components to the entity, as we can see in the entity baking preview at the bottom of the inspector. Fourth, after all the bakers have run, the systems of the baking world are run. Unlike the baker classes, the baking systems can be burst compiled and process the baked entities en masse, and the baking world systems are allowed to freely manipulate the entities, meaning create entities, destroy entities, set their components, add new components, or remove components. Note, however, that any entities created by the baking systems will not be included in the serialization. Now, baking systems are not usually needed in most simple use cases, but they can be useful when we want more control over the baking results or when what we want to bake may require heavy calculations. After the baking systems finish running, the last step of baking is to serialize the baking world. The product of this serialization is what gets loaded when the scene is loaded at runtime. Now let's look at creating a baker class. Say we have an iComponent data struct called movement, which we want to add to the baked entity in a subscene. To do this, we'll need a monobehavior, which by convention we'll call movement authoring, and then we'll define a baker class for this movement authoring. Note that nesting the baker class inside its authoring component is not required, but it's usually the logical place to put a baker. In the bake method of the baker, we first get the entity being baked, and then we add any components we like to the entity, in this case just the movement component. In simple cases like this, we typically just want to assign each field of the authoring component to a corresponding field of the entity component. The transform usage flags we pass to the getEntity method specify what transform components the entity should have. In this case, we want the entity to have a transform matrix for rendering, and we want to move the entity at runtime, so we use the dynamic flag. In another example, say we want an entity component that stores configuration parameters and prefabs. The entity field here called monster prefab references the prefab we want to instantiate, and the int field num_monsters specifies how many instances we want to spawn. In the baker's bake method, we can pass the GameObject prefab asset to getEntity, which will return the baked entity form of the prefab, which we can then assign to the monster prefab field of the iComponent data. Note that this getEntity call also registers the prefab asset to be tracked, such that if we modify the prefab, that will trigger a rerun of the baker. For other assets that a baker might depend upon, the baker should call the depends_on method to register the dependency. Modifying any registered asset will trigger a rerun of the baker. Other baker methods that register components include getComponent and getComponentInChildren, among others. Again, a baker will rerun if any of its dependencies are modified. Lastly, a baker can also call createAdditionalEntity to create more entities. Unlike entities created in baking systems, additional entities created by this method in a baker will be included in the serialization.